Welcome to the AI Research Roundup. I'm Alex. Today, we're looking at a paper trending on X, published on February 9th, 2026, about 5 days ago. It introduces a resource-efficient framework that boosts success rates in robotic manipulation by nearly 250% compared to the state-of-the-art Chi-0 baseline. The paper is titled Chi-0, Resource-Aware Robust Manipulation via Taming Distributional Inconsistencies. And as we'll see later, the system's ability to operate autonomously for 24 hours straight implies a significant step forward for real-world deployment. Alright, Figure 1 illustrates the full system. The top section shows the dual arms setup handling complex cloth manipulation tasks like flattening, hanging, and folding. Below that, the diagrams map out the core problem, a misalignment between the expert training data, the model's learned bias, and the actual test environment. To solve this, the framework uses 3 specific techniques: model arithmetic, train deploy alignment, and stage advantage to systematically align these distributions. The results are visible in the bottom right chart, where the yellow bar shows the success rate jumping to nearly 100%, far surpassing the baseline. Okay, Figure 2 details the specific pipeline steps for each distribution phase. On the left, dealing with training data, the system employs heuristic dagger and spatiotemporal augmentation to broaden coverage, while stage annotations break tasks into distinct phases like grasping or folding. In the center, the model section introduces model arithmetic, which merges weights from separate policies to combine their strengths. Just below that, the advantage estimator uses a vision language model to predict progress between state pairs. Finally, on the right, the deployment phase uses temporal smoothing and on-policy dagger to handle real-world deviations. Well, Figure 3 zooms in on the souping strategies for model arithmetic that we just mentioned. The top panel demonstrates the inverse loss technique, where individual policies are evaluated on a validation set. Specifically, the model with the lowest loss, shown here as the green bar L3, receives the highest weighting coefficient, alpha 3, in the final merged policy. The bottom row lists the 4 specific strategies the authors compared: average weighting, inverse loss, gradient descent, and greedy search. So, having covered model merging, Figure 4 demonstrates the second pillar, stage advantage. These charts track the cumulative value, or progress, over time for 3 distinct tasks. Green zones indicate smooth execution, while red zones identify failures. Specifically, the top graph shows a sharp dip where the cloth slips, followed by a recovery curve as the robot re-grasps it. This confirms that the advantage estimator acts as a reliable, dense signal for guiding the policy through complex recoveries. Alright, while Figure 4 focused on recovery, Figure 5 outlines the third pillar, train deploy alignment. The left panel illustrates 3 specific techniques used to bridge the reality gap. Topmost is heuristic dagger, where the robot is intentionally started in failure states to collect recovery data. Below that, spatiotemporal augmentation mirrors arm movements and scales timing to diversify the dataset. At the bottom, temporal chunkwise smoothing blends incoming action chunks to prevent jitter. The right panel confirms this works. The TSNE plots show the red model distribution and green test distribution gradually aligning with the blue training data as these methods are applied. Okay. After detailing the individual pillars, Figure 7 brings everything together to show the system efficacy on Task A. These charts break down performance by adding model arithmetic, stage advantage, and train deploy alignment one by one. The bottom left graph is particularly striking, showing the success rate climbing from about 25% with the baseline to nearly 100% for the full system. In the top left, we see a similar trend for throughput, which scales up as more components are combined. Ultimately, the yellow bars on the far right confirm that using all 3 pillars together yields the highest reliability. With the high success rates shown in Figure 7, Table 1 now lists the specific hyperparameters that drive this performance. The data and input section reveals that the method requires only about 20 hours of expert demonstrations per task, which supports the paper's claim of resource efficiency. In the optimization block, we see standard settings like 80,000 training steps and a batch size of 128. Finally, the infrastructure section at the bottom highlights the accessible hardware setup, relying on just 8 A100 GPUs for training and a single RTX 4090 for inference. Wrapping up, 2 takeaways stand out. First, achieving robust robotics does not strictly require massive compute scale. Second, by systematically aligning training and testing distributions, Chi-0 outperforms state-of-the-art models by 250% using only limited data. This suggests a promising future for resource-efficient autonomy. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.